should feel free to find me in my office. I've probably just forgotten about it. Okay, not that I could ever forget about a class as interesting as this one. See, I have to start saying different things once this thing starts recording. Okay, so today actually we're going to do what I think is really one of the high points of this course. So we're going to continue our discussion of renormalization in quantum electrodynamics. And in particular, what I want to, so far in this class, we've just considered the renormalization of propagators, that is to say, two-point functions. What I would like to today is to consider instead the quantum corrections, not to a two-point function, but rather to a three-point function. And in particular, what I would like to consider are the quantum corrections to the three-point function, which describes the interaction of an electron with a photon. So, in particular, what I would like to do is consider all of the quantum corrections to the vertex of this form, which that is to say, I would like to consider all possible Feynman diagrams which have two external electron legs and one external photon leg. So by charge conservation, one of the electrons has to come in, and the other, and an electron has to go out. So one arrow has to come in, and one arrow has to go out. And this vertex, this three-point function, carries a free index, a vector index associated with the photon, which I will call mu. And just for the sake of brevity, I will give a name to the sum over all diagrams of this type. I'll call it minus IE times capital gamma, where capital gamma is going to describe all possible quantum corrections to the electron-photon interaction. Okay. So this is the full quantum vertex describing all possible loop corrections to that three-point function. So, of course, at leading order, this vertex is just given by the tree-level interaction vertex, which is minus IE lowercase gamma of mu, so that what I called capital gamma is just given by a gamma matrix plus higher order corrections, where these corrections are some function of the various parameters in the problem. In particular, they're functions, say, of the electron mass, the electron charge, and the three momenta, p, p prime, and q. But, of course, q is equal to p minus p prime, so we can just write this as a function of m, e, p, and p prime. And they could also depend, say, on the gamma matrices, the metric, and that's it. That's all this can depend on. So gamma mu is a 4-vector, and it's also a Dirac matrix, so a 4x4 matrix, acting on the Dirac spinor index. So we can use Lorentz invariance, and in particular, the fact that gamma mu is a vector, to argue that it has to be the sum of three possible terms. So in particular, gamma mu is a vector, and it has to be built out of p, p prime, and lowercase gamma mu. And if you think about it, there's only a three-dimensional space of vectors that you can construct out of those quantities. So in particular, it has to be a linear combination of gamma mu, p mu, and p prime mu. So I'll just write a general linear combination like that. Okay. So here A, B, and C are 4x4 matrices that act on the spinor index. These are Dirac matrices. Question? Yes. Yes, one of those minuses should be a plus. Thank you. Let's call that one a plus. Good. Other questions? Sorry about that. Okay. So what I'd like to do now is further use the symmetries to restrict the possible forms of A, B, and C before I then go ahead and actually calculate these directly using Feynman diagrams. So the first thing that I would like to notice is that in an actual scattering process, gamma mu is going to be contracted with the external spinors describing the spin of the incoming and outgoing electron. So in particular, in any scattering process, so this was P and this was P prime, we actually have to contract with the external spinors. So I'll let U of P prime denote the spinor associated with the outgoing electron, and U of P be the spinor associated with the incoming electron on the left. And then in any scattering process, you actually end up not with gamma mu, but with the matrix element of gamma mu between those two spinors, those two four-component spinors. And then we can use the fact that these four-component spinors U obey various identities to simplify the form of A, B, and C. So in particular, as you hopefully remember from last semester, U obeys the fact that when you take P slash and act on U, you get M times U. And likewise, if you act on U of P with a P slash from the right, you also get just a factor of M. So what does this mean? So A, B, and C are scalars, so they have no vector index, but they are 4x4 Dirac matrices. And so in principle, A, B, and C could involve things like P slash or P slash prime, which are the only non-trivial Dirac matrices that you could construct from M, E, P, P prime, and gamma mu. But any P slash or P prime slash that appears in A, B, or C, you could always simplify using these two relationships here and turn them into scalars. And so that means that A, B, and C are just numbers rather than 4x4 Dirac matrices. And in particular, they are scalars, which are functions of M, E, P, P, and P prime. And if you think about it, the only scalars that you can write down that are non-trivial, that are functions of M, E, P, and P prime, are functions of E, M squared, and Q squared, which is P minus P prime squared. Because, for example, P squared is equal to M squared, P prime squared is equal to M squared. So the only non-trivial scalar quantity that you could write down that's not just proportional to 0 or M squared is Q squared. So that means that A, B, and C are scalar functions of Q squared. So A is some scalar function of Q squared, B is some scalar function of Q squared, and likewise C is some scalar function of Q squared. Now I've argued all of this just based on the symmetries of the problem, we're actually later on in this class going to head and compute this gamma, capital gamma, explicitly, and we'll verify it that indeed this is the case. But it's useful going ahead and using symmetries to constrain the possible form of the answer before we go ahead and start calculating anything. Now, the final point that I would like to make is that we can also use gauge invariance to simplify the answer. Because the Ward identity, that is to say, gauge invariance, implies that if you take this three-point function as a scattering amplitude, and you contract the free index associated with that photon with the momentum of the photon, then you have to get 0. So remember that gamma mu was gamma mu times A plus P prime mu times B plus P minus P prime mu times C, otherwise known as Q mu times C. And if you go ahead and contract those three structures with Q mu, so let's say, so if you contract, say, U bar of P prime gamma mu with U of P, then you get three different structures. So on the first, so coming from the A term, so what do you get? You get A, so actually, so let's contract that with Q mu. So what do you get? You get A times U bar of P prime gamma mu U of P times Q mu, which is P minus P prime mu. Okay. But if you use your spinor identities that P slash U is equal to 0 and U bar P slash prime is equal to 0, you can see that this, in fact, is M times U and U bar times M. You can see that this expression right here is just A times M minus M prime, which is equal to 0. Okay. So that A term is perfectly consistent with the Ward identity. Similarly, you have this B term. So what is that? That's U bar of P prime times P plus P prime mu times U of P, now contracted with P minus P prime mu. What is that? Well, P plus P prime times P minus P prime is P squared minus P prime squared, otherwise known as M squared minus M squared, which is equal to 0. So that's also equal to 0. So that B term is consistent with gauge invariance. The final term, however, is C times U bar of P prime times Q mu U of P Q mu. That is not equal to 0. In general, because Q squared is not in general equal to 0. If we have an external photon, then it's on shell, so Q squared is equal to 0. But if this is some internal photon in some scattering process, then Q squared is not equal to 0. It's some virtual photon. So that means that C has to be equal to 0 by gauge invariance. And indeed, that's something that we're going to check a little bit later on when we compute this explicitly, or at least when we compute one piece of gamma mu explicitly. So let me just summarize. So the electron vertex takes this form. So gamma mu is little gamma mu times A plus P prime mu times B. And what I'd actually like to do is simplify this a little bit using what's known as the Gordon identity. So the Gordon identity is something you're going to prove on the next problem set. And it's the statement that if you take the gamma matrix and you sandwich it between any two of these constant spinors, u and u prime, then you can actually replace that gamma matrix by the following quantity. You can rewrite it as u bar of p prime times, let's call it p mu plus p mu prime over 2m plus I sigma mu nu q nu over 2m all times u of p. Where here I'm using the notation that I introduced last semester when we studied gamma matrices, that sigma mu nu is the commutator of two gamma matrices, so it's a Dirac matrix. And it's a useful combination of these Dirac matrices because sigma mu nu is the generator of Lorentz transformations. So remember that on the representation of the Lorentz group defined by the Clifford algebra, defined by these gamma matrices, this bilinear, the commutator of gamma mu and gamma nu, is what we sometimes called S mu nu last semester. It's the thing that generates infinitesimal Lorentz transformations acting on these Dirac spinors. So I can put this all together to summarize our expression for gamma mu. It has to be the sum of two terms. I called these A and B up above, but I'm now going to rewrite them a little bit using this Gordon identity. So it's the sum of two terms, one of which is proportional to gamma mu, and the other of which is proportional to sigma mu nu over 2m times I times q nu times f2 of q squared, where f1 and f2 are linear combinations of those functions a and b that I wrote down above. The name of the game, then, is to compute f1 and f2. But before I do that, I just want to spend a few minutes talking about the physics of what's going on here, and physically how I should interpret these functions f1 and f2. So f1 and f2 are two functions that describe the quantum corrections to this electron vertex. They're quite important. They're usually known as form factors. And you should think of them as two functions that parameterize how the shape and the interactions of an electron are corrected by quantum corrections to the classical electromagnetism. So for example, at leading order, that is to say at tree level, f of 1 is just equal to 1. And f2 is equal to 0. That's just the standard electron vertex. However, what we've seen is that in general the symmetries allow f2 to be non-zero and f1 to not be equal to 1. Okay? And generally speaking, if something is allowed by symmetries, then it happens. And indeed, what we're going to see is that both f1 and f2 are non-trivial functions of q squared. But before I go ahead and compute them, I'd just like to spend a few minutes talking about the physical interpretation of these functions. Before I do so, let me pause and see if there are any questions. Yes?
Can you explain again why q squared equals 0?
Oh, q squared is not equal to 0. That's, sorry, not equal to 0. In general, q squared is not equal to 0. Because, if you have an external photon line, then it has to solve the equations of motion. And so photon is massless, so its momentum squares to 0. But if you have a virtual photon, okay, let's say you're studying electron-positron interactions or electron-electron scattering, then you just have a virtual exchange of a photon, which does not need to be on shell. That is to say, its momentum does not need to square
But
to zero.
in this situation, we're studying the external photon, right? We haven't-
Well, we didn't have to. Let's put it this way.
Okay.
We didn't have to. Okay.
So our initial vertex was just
Yeah. So in particular, what we're imagining is that anytime you see a vertex, an interaction vertex in QED, you could always replace that vertex by capital gamma mu. And that would describe the infinite tower of quantum corrections to that vertex in QED. In the same way that last week when we studied two-point functions and corrections to the photon self-energy, we imagined that, if you wanted to study quantum electrodynamics at higher order and perturbation theory, one of the things that you could do is replace this sort of standard classical propagator for the photon by the full quantum corrected propagator involving that function pi that we computed. Good question. Yes. Right. So this point that I'm making about q squared being non-zero is only relevant if I'm considering not an external photon, but an internal photon. Good question. Other questions? Okay. So first of all, what does this function f1 mean physically? That's easy to interpret physically. Anyone have any ideas? Can anyone tell me what f1 means physically? Well, let's remember how f1 would appear in an interaction. So at tree level, the interaction just says that gamma mu, or that the interaction vertex is the electron charge times gamma mu. So if you have the electron charge times gamma mu times some function of q squared, then that function of q squared could be interpreted as a correction to the electron charge. So f1 of q describes a momentum-dependent or energy-dependent correction to the electron charge. And indeed, we saw last week that there are energy-dependent effective corrections to the electron charge due to screening. And those are the sort of contributions that we could, if we wish, incorporate into the form factor f1 q squared. Is that clear? What's more interesting is the question of what f2 looks like, because it has a fundamentally different structure from f1. So it describes some fundamentally new type of interaction that an electron can have in QED once you start considering loop corrections. So in order to understand what f2 might mean physically, let's just think about what happens if we wish to study the theory at very low energies. So let's imagine that q squared is very close to 0. In this limit, the vertex, what does it look like? Well, it's just gamma mu times a number, f1 of 0, plus I sigma mu nu q nu over 2m times another number, plus terms that are higher order in the momentum. And if you think about it, this looks like an interaction term that comes from a correction to the classical Lagrangian. So remember that if you're describing the dynamics of an electron in QED, then, well, you have the classical kinetic term, which was I d slash minus m times psi. And then if you think about gamma mu as an interaction vertex, then it looks like it's an interaction between two electrons and a photon, which looks like it comes from some cubic terms in the Lagrangian. And what are those terms? Well, this first term, well, that just looks like the usual interaction term between an electron and a photon, which is E times psi bar gamma mu psi times, so that would be F1 of 0 a mu. Okay? So that it describes a three-point interaction between two electrons and a photon. And if you went through, as we did last semester, the Feynman rules coming from this interaction vertex, it would give you just this term right here. Okay. So that's the usual argument. I've just changed the constant that appears here from E to F1 of 0 times E. So you can really see that F1 of 0 is just a constant that looks like some correction to the effective electron charge. And what does that second term come from? So if you were to try and interpret that second term as coming from a term in the Lagrangian, what would it be? Well, you would have an E times psi bar times sigma mu nu times psi. And then you would have F2 of 0 over 2m. And every momentum q nu appearing in an interaction vertex comes from a derivative in the Lagrangian. Remember, derivatives in interaction terms lead to factors of momentum in the momentum space Feynman rules. So that I times q nu looks like a d by d nu of a mu. It's d by d nu of a mu because the momentum q nu is the momentum of the photon rather than of one of the electrons. So in fact, that can be simplified a little bit using the fact that sigma mu nu is antisymmetric in its two indices. This is actually d nu a mu minus d mu a nu, otherwise known as f mu nu. Okay. So this correction coming from the F2 form factor looks like some new interaction term in the quantum corrected action of quantum electrodynamics. Sometimes, so what I'm doing here is I'm taking the vertices that are appearing, including quantum corrections in Feynman diagrams, and reinterpreting them as if they came from an action. Sometimes the action that people write down that comes from this is called the quantum action. Sometimes it's even called the quantum effective action. We're going to be talking a lot more about effective actions later on in this course. For now, I just want you to notice that this interaction term F2 looks like it comes from a new term in the classical dynamics. And then, in order to understand how we should physically interpret F2, I'm going to look at how this term, this new interaction term, affects the dynamics of electrons and photons interacting, just at the level of the classical equations of motion. Any questions so far? So the question then is, what sort of corrections does this new interaction term right here lead to when you study it as a correction to the equation of motion of the electron? So the corrected equation of motion for the electron, well, that's just the Euler-Lagrange equations coming from this Lagrangian. So those are easy to read off, just vary with respect to psi bar, and you get the equation I d slash minus m let's see, I can actually, I believe there's a minus sign somewhere. It's actually not terribly important, so let's forget about it. But I believe there's actually a minus sign here because, yeah, I'll just try and be careful about my minus signs there. So minus E times A slash F1 of 0. And then we have the new term minus E over 2m F2 of 0 times F mu nu sigma mu nu acting on psi is equal to 0. So this is the quantum correction. This describes a quantum correction to the equation of motion of the electron. Any questions so far? Yes.
So to the previous question, so if it's a real photon, then basically Q squared is identical to 0, and we just have that.
That's correct.
So that if we limit ourselves to the
That's correct.
electron, that's
Yeah.
what we get.
That's right. I mean, there are these various ... terms here, that are the terms that are higher orders in Q. If you wanted to interpret those as corrections to this action L, they would be terms involving more and more derivatives. So these would be terms of lots and lots of derivatives appearing in the effective action, in this quantum effective action. They'll be there in general, but if you're only interested in low energy physics, then they're going to be irrelevant. So that's actually, if that's not obvious, don't worry. This is something we're going to spend a lot of time talking about, probably starting next week. The idea of effective actions and which terms are relevant at low energy and so forth. But I mean, up here I argued just by saying that, well, we're taking Q squared to be 0 because we want to study this process at very low energies. Good. Any other questions? Okay. So, in order to make a bit more sense of this equation, in order to compare this to our intuition about equations based on what we did in the very beginning of last semester when we studied the Dirac equation, what I'd like to do is remind you that any wave function psi that solves the Dirac equation also solves essentially a Klein-Gordon equation. It basically solves a Schrodinger equation as well. And by looking at that Schrodinger equation and looking at the various terms in that Schrodinger equation, we can come up with a very nice physical interpretation for the various terms that appear in this effective action for the electron. So this is something that we did at the very beginning of last semester, but I'm going to redo it here in a slightly more sophisticated way using the fancy Clifford algebra Dirac matrix notation. So what I'd like to do is remind you exactly how it is we see that psi solves the Klein-Gordon equation. So what I want to do is take this equation here and act on both sides of this equation with the following differential operator. So essentially what I want to do is I want to square that differential operator here appearing in the parentheses. So I'm going to act on it with ID slash minus E A slash F1 of 0. But then instead of having minus M minus E over 2M times that stuff, I'm going to have it plus M plus E over 2M. F2 of 0, F mu nu, sigma mu nu. And when I do that, so of course acting on the right-hand side just gives me 0. And from the left-hand side, we then see that psi is annihilated by the following differential operator. So I d slash minus E A slash minus M plus E over 2M F2 of 0 F mu nu sigma mu nu squared. All of that acting on psi is equal to 0. Okay, so why did I do that? Okay, well first let's just consider the case where the electron has no charge. Okay, just set E equals to 0. Then what would this be? This would be d squared minus m squared psi is equal to 0. And so that is the usual Klein-Gordon equation obeyed by a field of mass m. Now, I've added an electron charge here, and so I get these two non-trivial terms. Okay, I'm sorry, I forgot an F1 of 0 there. Okay, F1 of 0 you could just regard as part of the electron charge. But, okay, let's write it there. There's an F1 of 0. So let's just go ahead and compute those two terms. So first of all, what is I d slash minus E F1 of 0 times A slash squared? So did we actually do this computation last semester? We actually did it like the first or second lecture, not using the Clifford algebra notation, but using the alpha and beta matrices. I don't think I did it using did I do it using the Clifford algebra notation? I don't think I did. It's the same computation that we did in a slightly different notation in the first week of class. I'll just go ahead and remind you of how it goes quickly. So what is that? Well, let me rewrite that as I d mu minus E F1 of 0 A mu times I d nu minus E F1 of 0 A nu times gamma mu gamma nu and then what I'll do is I'll use the fact that gamma mu gamma nu can be written as the sum of the anti-commutator of gamma mu nu and the commutator of gamma mu nu. So what is that? That's 1/2 times the commutator of gamma mu with gamma nu plus 1/2 times the anti-commutator of gamma mu gamma nu. What is the anti-commutator of gamma mu with gamma nu? That's just the metric G mu nu. So this is equal to I d mu minus E F1 of 0 A mu squared. That just comes from the anti-commutator, because the anti-commutator of gamma mu gamma nu is twice G mu nu. Okay. So that's just the usual Klein-Gordon operator. Then we have a correction term proportional to the commutator of gamma mu with gamma nu, which I called I times sigma. So sigma mu nu is another name for I over 2 times the commutator of gamma mu with gamma nu. So this is I sigma mu nu times these two guys here. And then because sigma mu nu is antisymmetric in its two indices, I can just replace that by the commutator of d mu minus E F1 A mu with d nu minus E F1 of 0 A nu. Along with a factor of 1/2. Just using the fact that the antisymmetric part of this object right here is just 1/2 times the commutator of those two guys. And what is this commutator here? Well, d mu commutes with d nu, a mu commutes with a nu. So all that you're left with is the cross term, which is the commutator of d mu with a nu, i.e. d mu a nu minus d mu a nu, which is otherwise known as F mu nu, the field strength. Okay? This is E F1 of 0 times the field strength. Okay. So putting it all together, you get the usual Klein-Gordon kinetic term. Let's see, hopefully I got all the factors right. Okay, and there's, let's see, is there a factor of I somewhere? Did I miss a factor of I? Yeah, there's a factor of I here. Good. Which is going to cancel that factor of I right there. So I get E F1 of 0 times sigma mu nu F mu nu. Okay. So let's first just think about the case where F2 of 0 is equal to 0. Then we see that when you consider the Dirac equation, and you try and interpret it as a Klein-Gordon equation, it looks like the Klein-Gordon equation for a particle of mass m and electric charge E, that's what this term describes, plus this additional correction term here. Now, does anyone remember what that correction term is? We discussed it at the beginning of the semester. Okay. Well, if you don't remember, let me just remind you a little bit more systematically. Okay. So let's just go ahead and rewrite a little bit more carefully what this equation of motion looks like for psi. So the equation of motion says that I times d mu minus E a mu, okay, times f1 of 0 squared minus m squared plus this correction term. So we have sigma mu nu times f mu nu times E f1 of 0, and then coming from the first term when you expand out this guy, plus E over 2m f2 of 0. Sorry, there's no m there. Acting on psi is equal to 0. There's actually one more term here which comes from squaring this term here, squaring f mu nu, sigma mu nu. Okay, so plus dot dot dot. That term is higher order, so if you have a small electromagnetic field and you want to describe how an electron behaves in the background of an electromagnetic field, that term is generally going to be very small, so I'm just going to neglect it for the time being. And I think I missed a factor of 2 somewhere. Because in my notes I actually have an E over 2 here. Does anyone see where I missed a factor of 2? Let's see. Oh, it's because, wait.
You know, the definition of sigma, there is a 1/2 there.
There is a 1/2 in the definition of sigma. Oh, you're right. Okay, wait. That doesn't help me. Now I'm missing a factor of 4. Okay, you shouldn't have raised your hand. Let's see. Okay, there's some factor of 2. I'm pretty sure that factor of 2 is there. Okay, rather than spending my time trying to hunt down that factor of 2, let me just, so this is just a schematic argument to tell you the physical interpretation of F2. So I'm sure that somewhere when I mucked around with these commutators, I forgot a factor of 2 or 4 or something like that. Let's just put that factor of 2 in there and call it a day. I have a PhD. I'm allowed to do these sorts of things. You get permission to do that when you get your PhD. So let's just stare at this equation for a second. So look at these terms right here. So that's I d minus E a mu quantity squared. So what is that? That's the usual kinetic operator for a particle in an electromagnetic field. Remember in quantum mechanics, when you describe a particle with charge moving in an electric field or a magnetic field, you take P and you replace it with P plus E times A vector, where A vector is the magnetic potential. This is exactly the same thing. So this quantity here is the usual Klein-Gordon equation for a particle of mass m and charge q, charge E. And this term here describes a new sort of interaction. And it describes a coupling between the spin of the electron, as represented by that matrix sigma mu nu, and an electric field or a magnetic field in which you place the electron. So to simplify this, let's just choose a particular representation of the gamma matrices to work in. So let's use the Weyl representation. Remember, this is the one where our 4-component Dirac spinner just looks like a two-component spinner is written on top of one another. And in this notation, sigma mu nu just takes a very simple form. It's just a diagonal matrix. So sigma ij is epsilon ijk times sigma k along the diagonals. And sigma 0I is just I times the Pauli matrices along the diagonals. And so you can rewrite this equation. So what do you get? You get I d mu minus E a mu f1 of 0 squared minus m squared. That's the usual Klein-Gordon equation. Along with this correction, so you get a minus E over 2 times f1 of 0 plus f2 of 0 times, well, now we need to remember the fact that Fij is epsilon ijk times bk, and F0i is Ei. Okay? We want to write it in terms of the electric and magnetic field. So what do you get? You get B plus IE dotted in with sigma and B minus IE dotted in with sigma, all acting on our 4-component Dirac spinner, which we can write as two-component spinners right on top of one another. And remember that if you want to make contact with non-relativistic quantum mechanics, then we just take the limit where all of our momenta are small compared to the speed of light, and chi and phi in that limit become the usual 2-component spinners of non-relativistic quantum mechanics. This is the first thing that we did in this class. This was like the first week of the course last semester. So chi, for example, is a standard 2-component spinner in the non-relativistic limit. And then the question is, what does this additional term up here represent? Remember, these are particles with spin 1/2, and sigma represents the spin vector of the electron. And so if, for example, you set the background electric field equal to 0 and just studied the electron in the background of some magnetic field, then a B dot sigma term in the equation of motion, in Schrodinger's equation, is interpreted as a coupling of the magnetic field to the magnetic moment of the electron. So this form factor F2 is describing a quantum correction to the magnetic moment of the electron. In particular, we usually characterize a magnetic moment by a parameter mu. So the magnetic moment is usually denoted mu, and it's usually characterized by a parameter g, which is called the Landé G factor. So this is just a rewriting of the coefficient of B dot sigma, okay, in terms of a new parameter g. And g so if you just set F2 of 0 equal to 0, then g would be precisely equal to 2. If, for example, I interpret F1 of 0 as just being incorporated into the electric charge, F1 of 0 is just part of the electric charge, then in classical electrodynamics, in the classical equation describing the coupling of the electron to some background electromagnetic field, the magnetic moment is described by this quantity here with G is equal to 2. And you see that once you include quantum corrections, you get a correction proportional to F2 of 0. So F2 describes the corrections to the magnetic moment of the electron. F2 of 0 describes the very long distance correction to the magnetic moment of the electron. And F2 of q squared could, I suppose, be regarded as the momentum-dependent corrections to that magnetic moment. I should make one comment here. So this, I believe, is something that we discussed at the very first week of this course when I was trying to motivate quantum field theory. At leading order, when you neglect all of the quantum corrections, G is equal to 2. So this Landé G factor is introduced so that a charged sphere has G equals to 1. So remember, whenever you have a charged object that's not a particle but has some extent, if you give that object some spin, it'll have a magnetic moment. So if you take a charged sphere with uniform charge distribution and you start spinning it, then it'll have a magnetic moment that is proportional to its angular momentum. And the Landé G factor for just a charged sphere is equal to 1. And so the fact that you get a 2 here, just using the Dirac equation, is already telling you something about how, in special relativity, the internal structure of an electron is constrained in some way. It's constrained so that G is equal to 2 rather than equal to 1. Now, what we're doing when we can construct the corrections to the electron vertex using quantum correction is we're calculating the corrections to the further quantum corrections to the magnetic moment of the electron. Or if you want to think about it a little more schematically, we're computing the quantum corrections to the shape of the electron. In the sense that G equals 1 is a perfect sphere, G equals 2 describes some other shape, we're describing quantum corrections to the shape of the electron more generally. Yes?
So F2 of 0 is negative or positive?
It's going to be positive. One other comment that I'll make, actually, just from an experimental point of view. If you take a particle with spin and a magnetic moment, if you take a particle with both a charge and a magnetic moment, and you put it in a magnetic field, then there are really two kinds of oscillating behaviors that you can associate with that. If you just take a particle without a magnetic moment and you put it in an electric field, it'll move around in a little circle at a particular frequency called the cyclotron frequency. You guys have hopefully seen this. This is what Landau levels are. They're particles that move at the cyclotron frequency. And if you put a particle with a magnetic moment in a magnetic field, then it'll oscillate, okay, with some characteristic oscillation frequency. And when G is equal to 2, that implies that the cyclotron frequency is equal to the spin precession frequency. When you put it in a magnetic field. So that actually, from an experimental point of view, means that corrections to G equals 2 are actually very easy to measure. Because if you can measure if you have two frequencies that are very slightly different, that's something that's typically easy to measure experimentally. So in fact, G minus 2 is probably the best measured constant in physics. I believe it's measured to 13 decimal places. And I think this probably holds the record for the most precisely measured fundamental constant in physics. So it's the best measured quantity in the history of physics. So it behooves us to try and calculate it theoretically and see how well we can match that experimental measurement. Okay, here, maybe for the sake of drama, let me just write down what it is experimentally. So I just looked this up before class. So experimentally, G is 2.002319304,361. And the last digit, 7, has some uncertainty, plus or minus 3. So I guess, what is that, 12 digits? So, okay, so let's see how we can go about calculating this theoretically. So before I do so, let me pause and see if there are any questions. Okay. So I can probably do that. Any questions before? I'm rolling on my sleeves. Any questions before I go ahead and compute G minus 2 for the electron? So in fact, the techniques that I'm going to use to calculate G minus 2 are no different from the techniques that we introduced last week and the week before in order to calculate other quantities in quantum electrodynamics. In fact, it's even somewhat, the algebra is more tricky, but conceptually it's easier because actually for this quantity no renormalization or regularization is needed. It's just a loop computation. So let's go ahead and compute G minus 2 at one loop. Jesus Christ. Okay. So this is the set of diagrams that we're trying to compute. So at one loop, there are 4 diagrams that contribute to this. Sorry, I'm not showing that very well. So there's one diagram where you have an electron loop in the photon propagator. There are 2 diagrams where you have photon loops in the electron propagator. And then there's one diagram where you have an electron connecting those 2 external photon connecting those 2 external electron legs. So the first thing to notice about this is that these first 3 terms give you corrections to propagators. In the first case, a correction to the photon propagator, which we computed last week, and in the next 2 cases, a correction to the electron propagator. But because these only contribute to the propagator, they only contribute to F1. In particular, you always just get a gamma matrix associated, a gamma mu associated with that interaction vertex. So you'll never get this new kind of tensor structure where you have a sigma mu nu F mu nu. So those 3 terms, those 3 Feynman diagrams, well, at the end of the day, you might end up needing to compute them if you want to compute all of the form factors. But it's only this last diagram that contributes to F2. So let's go ahead and compute it. So here, as before, I'll call the incoming and outgoing electrons momenta P and P prime. Actually, you know what? In my notes, I called them P1 and P2. So that's what I'll call them here. I'll call them P1 and P2. The external photon leg has momentum Q, which is P1 minus P2. And let's call this guy momentum K, so that then this has momentum K minus P1, and this guy has momentum Q plus K. Now it's a straightforward exercise to go ahead and write down this diagram using our Feynman rules. So I'll just go through this rather quickly as sort of an exercise in using some of the computational techniques that we have been introducing over the last few weeks. So what do you get? So it's going to be a rather lengthy expression. So you get 3 powers of E, because it's there are 3 electron interaction vertices. You have to integrate over the undetermined loop momentum K. And then what do you have? Well, let's start with the photon propagator down at the bottom of this diagram. So that gives you a 1. So remember, the photon propagator is g mu nu over q squared, where q is the momentum of the photon. So that's going to be g, let's call it nu alpha, because mu is the free index up here. So I'll call the index here nu, or maybe I'll call the index here nu, and I'll call this index alpha. So you get a g nu alpha over k minus p1 squared minus I epsilon. So for the sake of making life a little simpler, I'm just going to not bother writing those I epsilons. Okay, now we have to write down all of the Dirac factors. So you start down here with the outgoing electron, and you have that spinner u of p2 bar, and then you have this vertex right here, which is a gamma nu, and then you have the q plus k electron propagator. So that gives you, sorry, I left out an I here. There's I's in all of those propagators. I times q slash plus k slash plus m over q plus k squared minus m squared. So that's 1 electron propagator. And then we get a gamma mu coming from this vertex. And then we get another electron propagator from the electron with momentum k. So that's I k slash plus m over k squared minus m squared times u of p1. And now it's straightforward but a little bit tedious to go ahead and compute this thing. So in particular, we have 3 denominators. I'm not going to go through all of the computation. I'm just going to highlight sort of the strategy and tell you the basic details, because from this point on, it's more or less algebra. So to simplify those denominators, we use the Feynman's denominator formula, which I think you proved on your last problem set. We use it for 3 denominators, so you get an integral dx, dy, dz, with a delta function that sets x plus y plus z equal to 1, times 1 over x times a plus y times b plus z times c cubed, because we're combining 3 denominators. And a is going to be this denominator, b is going to be this denominator, c is going to be this denominator. So that quantity that appears in the denominator, well, we can just write it out. It's pretty easy. You get a k squared times x plus y plus z from the a, b, and c terms, which sums up to 1. So you get a k squared. Then you have the terms linear in k, so plus 2k dot from a, you get minus z. Okay, I think I might have called these different things in my notes. I might have relabeled what I called A and B and C. Okay, that first term, yeah, I think in my notes, okay, let's make life simple. In my notes, I called this C and this A. It's just a relabeling of what I mean by A, B, and C. Yeah. Yes. There was a final vertex gamma alpha. Thank you. Good. Okay. So sorry, I just, in my notes, I think I've written them down in a different order. So I guess A is k squared minus m squared, B is q plus k squared minus m squared, C is k minus p1 squared. So what do you get? You get 2k dot yq minus p1 minus z p1. Okay. And then you get a y q squared term and a z p1 squared term, and then two mass terms coming from the a and b. So you get minus x plus y times m squared. And then we want to make the d4k integral invariant under four-dimensional rotations. So we complete the squares and write this as L squared minus delta, where L is the thing that you get by completing the squares between these two terms. So L is k plus yq minus z p1. And then you can use that L to go ahead and solve for delta. So delta, well, it's straightforward enough to work out. I'll just tell you what the answer is. It's minus xy times q squared plus 1 minus z times m squared. And then it's straightforward to go ahead and work out what the numerator is, writing everything in terms of L. So in terms of L, the numerator, so after some algebra, I'm not going to go through the algebra for you. So there's some algebra. You have to use that Gordon identity that I wrote down for you earlier. The numerator, what is it? Well, there's one term that's interesting. So you get a u bar of p2 times sigma mu nu, that came from the Gordon identity, times u1 of u of p1 times I m z times 1 minus z times q nu, plus a bunch of other stuff. So the other stuff that you get, well, actually maybe I'll just tell you. Well, you get u of p2 bar times gamma mu of u1 bar, okay, times some stuff. So that term is going to contribute to F1. That's the first form factor that describes the normalization of the electric charge. Okay. We're not interested in that one for now, so I'm just going to forget about that term. And then there's a second term that has a u2 bar u1 times q mu times some other stuff. So there's a z minus 2 and an x minus y. So that term would apparently lead to a contribution to the electron vertex that's proportional to gamma mu. But I argued earlier in this class that that quantity, which I called capital C, had to be equal to 0 by gauge invariance. And in fact, you can check that, well, you have an x minus y here, but this integrand up here is invariant under interchanges of x and y. And likewise, delta here is invariant under interchanges in x and y. So you have an integral of a symmetric integrand dx dy of x minus y, which is antisymmetric under the interchange of x and y. So this actually integrates to 0. As it had to by the Ward identity. And so what you're left with is just a contribution coming from this term to F2. So let me just put this all together for you. So we conclude that f2 of q squared, well, what do we have? So in the definition of f2 of q squared, there was a factor of e over 2m. So this is just some factor that was part of our definition of f2. And then if you work out this, put together all of the terms that I wrote down above, let's see, you get an e cubed, and then you have this term. So we're looking at this term here. There's a factor of m we can pull out front. And then you had an integral dx, dy, dz times this delta function. That says x plus y plus z equals to 1. And then we have this integral d4L over 2 pi to the 4th. You get a z times a 1 minus z over L squared minus delta, all cubed, coming from that denominator formula, where delta was minus xy times q squared minus 1 minus z squared times m squared. Okay. Now let's see. Okay. Yeah, I actually have a factor of 4 in my notes. It's not too important. I mean, I'm not keeping track of all of the details. You know, if you're Feynman, Schwinger, Tominaga, it's important to keep track of all the details because then you're going to win a Nobel Prize for this calculation. For us, I'm not going to worry too much about an overall numerical constant. The important point is that the d4L integral is convergent, right? Because it's an integral d4L with 6 powers of L in the denominator. So that's an integral that you can just do, and I think it's one of the integrals that you're doing this week on your problem set. So that's just, well, I'll just tell you the answer. It's minus I over 32 pi squared times delta. So then if you put this all together, you get an answer for f2 of q squared in terms of that integral dx, dy, dz. So it's proportional to e squared, and so it's traditional to write it in terms of the fine structure constant, which is e squared over 4 pi. So it's the fine structure constant. There's another pi in the denominator, okay, because of that pi squared. And then there's an m squared. Yeah, I think this must have been an m squared. There's an m squared. Oh, I'm sorry. No, it's an m. But there's an m squared. There's one m here, one m there. And then we just have some numerical factor. So an integral dx, dy, dz times that delta function times z times 1 minus z divided by xy times q squared minus 1 minus z squared times m squared. So there you have it, a reasonably explicit answer for this form factor that describes the corrections to the interaction of an electron with a photon at loop order in QED. In fact, at q squared goes to 0, all of the complicated terms in this denominator cancel out, and you're left with a very simple integral. So you just get an integral dx, dy, dz of that delta function of z divided by 1 minus z. That's a straightforward integral to do. It just gives you actually a factor of 1/2. And so you get f2 of 0 is given by alpha over 2 pi. Okay. So now you use the fact that alpha is 1 over 137, and you plug that in to your expression for g, which was 2 times 1 plus f2 of 0. And you get 2.00232. So that is the one loop correction to the magnetic moment of the electron. Okay, so let's go ahead and compare to our experimental result. So there you go. We just got those terms right there. Oops. Actually, no, we didn't get that 9. We just got those first 5 digits there. My pen has stopped working. Okay. Still working? Still not working. Okay. In any case, yeah, my pen really has stopped working. Did I finally break it? Okay. In any case, you can see here, no, it's erasing fine. It's just not writing. Okay. Well, I'm done. I did sort of want to scroll down one more time to wax poetic. Maybe. I can't. Okay, there you go. I do want to scroll down one more time to wax poetic. Okay. So we've computed here, I mean, this is probably the most important calculation in quantum field theory, at least historically, because this calculation of the anomalous magnetic moment of the electron, along with the calculation I presented last week of the quantum field theory contribution to the Lamb shift in the hydrogen atom, these are really the two calculations that established quantum field theory as a useful tool in physics, as a predictive, useful way of studying the interactions of fundamental particles. Maybe I'll make one comment, actually, which is that it's sort of interesting. I told you that theoretically, I told you that experimentally G minus 2 can be measured to 13 decimal places. So you might wonder how well we could match that theoretically. So it turns out that one can perform, so this QED correction to the magnetic moment has been done up to 4 loops in quantum electrodynamics. It's actually, 4 loops might not sound like much, but it's actually an incredibly difficult calculation. Interestingly enough, the error on the biggest error on the 4-loop theoretical calculation in QED comes from the fact that we can't do the integrals analytically. You have to do them numerically using what are known as Monte Carlo methods. Nobody actually, there are no closed form expressions for the integrals, and so the largest theoretical error on G minus 2 actually comes from the fact that we just there's numerical error when we do those integrals. Okay. And when you're working at 13 decimal places, this is the sort of thing that matters. Another comment that I'll make is that when you're working at such high degree of accuracy, not just quantum electrodynamics comes into the game. You have to consider all of the other elementary particles and their various form factors and things like that. So you actually, if you want to compare that experimental result to the theoretical result, then you actually have to feed in as input parameters a lot of other data about other sorts of particles and other sorts of physics. But in fact, theoretically, people have also computed G minus 2 doing all of these things to 12 significant figures. And this is probably the most precise match between theory and experiments in the history of physics. I mean, aside from trivial things that are 0. Okay? Like, you can check 0 to lots of decimal places. But actually, that's not even always true. But I think that this computation is a fair claim for being the greatest match between theory and experiment in the history of physics. Okay? So my pen is still not working, so I can't actually do anything else. Well, I don't know. No. Yeah. Okay. I don't know how to stop it from recording without this pen. But maybe I'll just stop here and see if there are any questions. Any questions on this? I mean, I skipped a bunch of steps in the calculation because it's exactly like calculations that we did a lot last week, so I didn't necessarily, just a little grungier. But I just wanted to give you a flavor for how the calculation goes without spending a whole lecture going through all of the algebra. Any questions before I stop here? So we might spend one or two more lectures on QED before diving a little bit more generally into the features of normalization more systematically in quantum field theorems. Okay, I will see you on Thursday. For a higher spin particle? What do you
Let's
mean
say the 3-point
precisely?
function of like a spin 3/2 particle.